Hi everybody, this is Dr. Nageswara, Assistant Professor of Physics, SRR Xavier Autonomous Government Degree College, Vijayawada. Today we will discuss about Raman effect. We know C.V. Raman is one of the famous scientists of physics in India and also first Nobel Prize winner in physics from Indian origin. So Raman effect having numerous applications in molecular physics. So today we will discuss about what is Raman effect, what are the applications of Raman effect, what is its experiment. Raman effect is widely used in the study of vibrational properties and rotational properties of molecules. We know ordinary in case of light which is passing through the transparent material like a crystal, it is scattered into different colors. In case of it is potassium chloride crystal, or prism, when the white light which is entered into the crystal or maybe called prism, it is divided into 7 colors. This is called scattering window. So when a beam of light which is passing through a not only solid and also a liquid or a gas or any transparent substance, some fraction of light is scattered in all directions. But according to Rayleigh, when the light is passing through the material, if it is monochromatic, the scattered light having only one frequency, that is incident light. It is nothing but there is no scattering occurs. What frequency of light which is incident on the crystal, the same frequency will be scattered on the second side. So this is called Rayleigh scattering. But according to Raman, when the light is incident on the transparent materials or liquids or gases, the scattered light having different frequencies other than incident light. This phenomena is called Raman effect. These scattered light having weak lines of changed frequencies. This frequency may be greater than incident frequency or less than incident frequency. Depending on that frequency, Raman lines divided into 2 lines. That is Stokes lines and anti-Stokes lines. These additional lines are called Raman lines. Of course, this phenomena is called Raman effect. These lines occur symmetrically when in this is diagram. This is actually central line, that is called incident line. When this light is incident on the transparent material, this line is split into 2 lines. One is this frequency. This is less than incident line frequency. And this line frequency is more than the incident line frequency. The central line frequency is not changing. So this is also called Rayleigh line or Rayleigh scattering. While those lines are having higher frequency side, these are called anti-Stokes lines. Where these lines are having lesser frequency than incident line are called Stokes lines. So there is two Raman lines we observing. One is Stokes lines whose frequency is less. It means whose wavelength is more than the incident light. Because we know wavelength is inversely proportional to frequency. That is, we know the formula mu is equal to V is equal to mu lambda, or mu is equal to V by lambda. That is, V and lambda or mu and lambda is inversely proportional. In case of Stokes lines, the frequency is less, is nothing but the wavelength is more. In case of anti-Stokes lines, whose frequency is more, so that wavelength is less. So Stokes lines having less frequency and higher wavelength, and anti-Stokes lines having more frequency and a lesser wavelength. What are the characteristics of this Raman effect? The frequencies of Raman lines are depending on the frequency of the incident light. The frequency of Raman lights are depending on the frequency of the incident light, but does not depending on the nature of the material. But the Raman shift, that is also called displacement of Raman line, which is depending on the nature of the scattering material. That is, maybe it may be a benzene, or maybe any liquid, or maybe gas, any transparent material. When the material changes, the Raman displacement, the Raman shift also changes. Lines having frequency less than this exciting line or incident line are called Stokes lines. Already we discussed earlier, and this is also one of the characteristics of the Raman effect. Another characteristics, we know already we know about the anti-Stokes lines. For each anti-Stokes lines, the frequency is more and hence wavelength is less. Anti-Stokes lines always weaker than Stokes lines. It is nothing but the intensity of anti-Stokes lines is lesser than the Stokes lines. And a rotational state or vibrational state of molecule is changed due to scattering of light, because Raman effect is always is a molecular spectrum it represents. Raman effect is purely a molecular phenomenon. It does not related with the atoms. Raman lines are strongly polarized. We know at second year level, we discussed about polarized light. That is circularly polarized light, plane polarized light, elliptically polarized light. Similarly, these Raman lines are strongly polarized. Raman lines are symmetrically distributed among the incident line. We know the central line is incident line. Both sides at the same distance, these Raman lines are symmetrically distributed. Raman shift, that is nothing but the difference between incident light and the Raman line frequency. That is called delta nu is called Raman shift. Of course, what is this experimental phenomena of Raman effect? Of course, Raman effect got in Nobel Prize in Physics very fast from India. But the equipment cost, Raman said the total cost of this equipment is around 400 rupees only at that time. But the quality of research is very important. The cost of the equipment is not much. So, in this experiment, what we have? This is the experimental setup of the Raman experiment. It contains a source. It may be give monochromatic light, or maybe any white light, or maybe multiple source. And second was the Raman tube. And third one is spectrograph to observe the scattered light. In this, S is the source of light. This S is the source of light. This is when we are giving some energy, the energy will be liberated from this mercury lamp. It is nothing but that it gives white light. This white light is just passing through the filter. Yeah. Filters may absorb some of the wavelengths and it emits some of the wavelengths. So, due to this nature of this filter, we will get the monochromatic light. What is meant by monochromatic light? Monochromatic light is nothing but it contains a single wavelength or single color. The monochromatic light then passes through the metal reflector and then enter into the Raman tube. So here C is the Raman tube. This is the Raman tube. So when this light which is entered into the Raman tube. Raman tube having a diameter around 1 centimeter to 2 centimeter. This is actually 1 centimeter to 2 centimeter, whose length is around 10 centimeter to 15 centimeter. Actually, this was filled with the required material that may be liquid, or may be gas, or may be transparent solid material. The other end is when we observe here, there's one end is here scattered light will come outside, and there is a flat glass surface. This right side is a flat glass surface, and the second end is there is just like horn type shaped blackened outside. Because if it is blackened paint, the light is reflected back. The tubes get overheated in sometimes because of the atoms excitation. So that to overcome that heat, we will use water jacket. So through this jacket, water will flow, cold water will flow. So the temperature of this tube will maintain at the required temperature. The sample material is placed inside this tube, Raman tube, and a scattered beam which is emerging from the flat end of the Raman tube. So this from this end, the light rays or scattered rays will come outside. This can be examined by using the spectrograph spectrometer. When the sample is gas, it is enclosed in a Raman tube with a few centimeters of mercury pressure. If it is solid or a powder shaped, it is mixed with the either paraffin or any other solvents to the for getting the proper scattering. So this is the experimental setup of Raman effect, and how can we get scattering light and observe through spectroscope or spectrograph. How can we explain this Raman effect? Quantum theory is very, very good to explain the Raman effect. So how can we? We know according to the Planck's quantum theory, the light is emitted in the form of quanta, are also called photon. We know each photon having energy h nu, that is in school education days onwards, we are discussing about that energy is equal to h nu. So here also we are having energy is equal to h nu naught. E is the energy of the photon, h is the Planck's constant, nu is the nu naught is the frequency of the incident light. So there is a three types of scattering we may observe according to this diagram. When the photon is collided with the molecule inside the Raman tube, there may be three things happen. In some of the case, the frequency does not change. That is when h nu is coming outside, when the h nu is the frequency of the incident photon, and outside photon also h nu. It is nothing but the scattered photon frequency is also h nu. It is nothing what we said. It is saying that the frequencies are does not changing. This is called Rayleigh scattering. This is incident beam. Same incident beam will come outside after scattering. But in this case, when you observe left side, h nu is the frequency of the incident light. In this case, h nu naught is the scattered light. In this case, lambda dash is less than lambda is nothing but nu dash is greater than nu. The frequency is more. It is nothing but anti-Stokes lines. When you observe the right side, this actually h nu is the incident photon and h nu dash is the scattered photon. So in this case, lambda dash is greater than lambda is nothing but nu dash is less than nu. That is, incident photon frequency is more than the scattered photon frequency. This is called Stokes lines. So these three will be happening in this case of Raman scattering. Why it is happening? The first case, that is nothing but Rayleigh scattering, that is called unmodified scattering of incident light. Because when the photon is incident on the material inside the Raman tube, the energy did not absorb from the molecule and also did not give it to the molecule. So the photon, incident photon, does not absorb or does not emit energy, and hence there is no change in frequency. This is called unmodified line in the scattering beam. So this was shown in this diagram. The wavelengths are equal as well as frequencies also equal. This is called unmodified Raman line. And the second one, when the photon as incident photon is incident on the excited molecule, it may emit some of the energy to the incident photon from the molecule. Because the molecule is already in the excited state, it is nothing but it has more energy. That more energy will be given to the incident light photon. Then what happens? The energy of the photon increases. So the scattered photon energy increases is nothing but the frequency also increases. The frequency increases is nothing but that is called anti-Stokes lines. Now, the energy of the molecule decreases and increases the energy of the scattered photon. Where E1 and E2 are initial and final energy of the molecule inside the Raman tube, then the total energy of the photon is h nu naught plus E1 minus E2. Of course, from this, the frequency may be written as nu AS is equal to h nu naught plus E1 minus E2 by h, because h nu is h, that is the energy of the photon. Nu AS is nothing but anti-Stokes lines. AS represents the anti-Stokes lines and nu represents the frequency, simple, where AS is anti-Stokes lines. And third case, in this case, when the incident photon is incident on the material or maybe excited the material, it absorbs, it gives the some of the energy to the atom. Now, the energy of the molecule increases and decreases the energy of the scattered photon. So what is happening here? The incident photon is when incident on the molecule may absorb some of the energy of the photon. So when the photon will give some of the energy to the molecule, the energy of the photon decreases. That is nothing but frequency also decreases. Frequency decreases is nothing but that is Stokes lines. So Vs, nu S is nothing, Vs is Stokes, nu S is nothing but the frequency of the Stokes lines. The frequency of the Stokes lines, nu S is equal to nu naught minus E1 minus E2 by h. That is the represents the frequency of the Stokes lines. This shows that frequency of a scattered line in is decreases and hence this is called Stokes lines. What are the applications? Not only here, any topic. When we discuss, there is some use is required. Those are called another name applications. So the one of the best application of Raman effect will be used in telecommunications. Not only that, in optics, supercontinuum is formed using the Raman spectra, which results in smooth spectra as the initial spectra are filled spontaneously, which is later amplified to higher energy. And also, this Raman spectra is much useful where the lower frequency DNAs are and proteins are studied and chemistry to understand the structure of molecules and their bonds. So, to study the DNA in biology and medicine and proteins in chemistry, we will use this Raman spectra. And Raman spectra is used in remote sensing and planetary exploration. And Raman spectra is used to sense the minerals in moss. And Raman effect I used to study the molecular structure of crystals and compounds. What kind of molecular structure? What kind of bond is there? What is this bonding energy? We cannot study. And also to study the composition in plastic materials and mixtures also, we can use this Raman scattering. Raman scattering is used to estimate the single bond, or double bond, or triple bond in any molecule. It is used to study the spin and statistics of nuclei. And of course, it is the main importance of nowadays and is the vibrational and rotation energy levels of homonuclear molecules like nitrogen, oxygen, etc. So these are the some of the applications of Raman effect we observed until now. Thank you very much.